The Kripke-Platek axioms of set theory, pronounced ḳrpki placed tk, are a system of axiomatic set theory based on the ideas of Saul Kripke and Richard Platek. Kp is considerably weaker than Zermelo Fraenkel set theory, and can be thought of as roughly the predicative part of ZFC. The consistency strength of Kp with an axiom of infinity is given by the Bachmann-Howard ordinal. These restrictions on the axioms of Kp lead to close connections between Kp, generalized recursion theory, and the theory of admissible ordinals. The axioms of Kp. Axiom of Extensionality. Two sets are the same if and only if they have the same elements. Axiom of Induction Phi being a formula, if for all sets X, the assumption that Phi holds for all elements Y of X, entails that Phi holds, then Phi holds for all sets X. Axiom of Empty Set. There exists a set with no members, called the empty set, and denoted, is implied in certain formulations of first-order logic, in which case the axiom of empty set follows from the axiom of separation, and is thus redundant. Axiom of Pairing. If X, Y are sets, then so is X, Y, a set containing X and Y as its only elements. Axiom of Union. For any set X, there is a set Y such that the elements of Y are precisely the elements of the elements of X. Axiom of sigma-zero separation. Given any set and any sigma-zero formula Phi, there is a subset of the original set containing precisely those elements X for which Phi holds. Axiom of sigma-zero collection. Given any sigma-zero formula Phi, if for every set X there exists a set Y such that Phi holds, then for all sets U there exists a set V such that for every X in U there is a Y and V such that Phi holds. Here, a sigma-zero, or pi-zero, or delta-zero formula is one all of whose quantifiers are bounded. This means any quantification is the form awesome, but not all authors include an axiom of infinity. These axioms are weaker than ZFC as they exclude the axioms of power set, choice, and sometimes infinity. Also, the axioms of separation and collection here are weaker than the corresponding axioms in ZFC because the formulas Phi used in these are limited to bounded quantifiers only. The axiom of induction in Kp is stronger than the usual axiom of regularity. Proof that Cartesian products exist. Theorem. If A and B are sets, then there is a set A times B which consists of all ordered pairs of elements or of A and B. B. Proof. Equals A exists by the axiom of pairing. B exists by the axiom of pairing. Thus equals B exists by the axiom of pairing. If P is intended to stand for, then a delta-zero formula expressing that is, and thus a superset of A times B equals A in A exists by the axiom of collection. Abbreviate the formula above by then is delta-zero. Thus A times B itself exists by the axiom of separation. If B is intended to stand for A times B, then a delta-zero formula expressing that is, thus a superset of A times B in B exists by the axiom of collection. Putting in front of that last formula and we get from the axiom of separation that the set A times B in B itself exists. Finally, A times B equals A times B in B exists by the axiom of union. QED. Admissible sets. A set is called admissible if it is transitive and is a model of Kripke-Platek set theory. An ordinal number alpha is called an admissible ordinal if L alpha is an admissible set. The ordinal alpha is an admissible ordinal if and only if alpha is a limit ordinal and there does not exist a gamma less than alpha for which there is a sigma 1 mapping from gamma onto alpha. If M is a standard model of Kp, then the set of ordinals in M is an admissible ordinal. If L alpha is a standard model of Kp set theory without the axiom of sigma-zero collection, then it is said to be an amenable set.